Hello everyone, I'm Dr. Fawzul Atik. I'm giving some series of lecture for the course Probability and Statistics. We are in the chapter of joint probability distribution. We have done a couple of examples. So in today's class, we'll discuss about the sum of two independent random variables. Right? So what is that? First, we'll talk about the discrete random variable, sum of two discrete random, and then later we'll talk about the continuous sum of two continuous random variables, which are independent. What is that? For two independent discrete random variable x and y with probability mass function PMF, Px and Py, the probability mass function of their sum W equal to x plus y. What is that value? We will try to get it. And we'll see that we will get the PMF of their sum W equal to x plus y with the help of convolution property, convolution of their individual PMF. So how we can think of it? So we need to calculate basically P of W equal to small w, right? Probability mass function of the joint of their sum. Now what is W? W is basically x plus y, right? W is basically x plus y. So we have to find out all xy value. So we have to find out all xy pair such that x plus y equal to w. So then if we take like if you do in that way, so probability mass function of w is equal to basically p of w equal to w, and then it is basically x plus y is equal to w. Now is it not? We have to do, there are several x and y, right? For which x plus y will be equal to w. So if I do that p of capital X is equal to x, then what is the value of y? Y is equal to w minus x. So then y is equal to, we can have small w minus x. But is it true for only one x? It is true for several x, right? So what basically we are doing, we are trying to find out all such xy for that x plus y equal to w. So you take x is equal to x. Therefore y equal to w minus x. And then we have to consider all such x such that y equal to w minus x. So then this will be equal to sum of their probability, right? So sum over x. So if you take all such x such that x is equal to x and y equal to w minus x, then definitely for all such x, x plus y equal to w. Therefore, we can have this thing. Now, one more thing, it is also given that x and y are independent discrete random variables. So if x and y are independent, what we can say? We can just separate them out, right? So this is actually x is equal to x and y equal to w minus x, but x and y are independent. Therefore, I can write it as that. We can write it as p of x is equal to x into p of y is equal to w minus x. And what is that? They are actually the marginal probability mass function of x and marginal probability mass function of y. So we can write it as x into small p of y of w minus x. Right? So this property, this result is known as, this is basically we got as p of w, that we are getting the probability mass function of w, which is the sum of x plus y. This property is known as the convolution, discrete convolution of rho x and px and py of their marginal PMF, right? So we are going to use this in some other examples. Yeah, so whatever we have done, it is also written in very formally. You may take a snap of it. And then in today's lecture, we'll be mostly giving something that you should know. We may not go much details of it, but you should know that what will happen for like individual. We have discussed that okay, join individual that PMF of the sum, probability mass function of their sum, it can be given by the convolution property. Then we will take that x and y are different kind of discrete random, and we'll see what is their sum. So to discuss that, first we will discuss that x and y are binomial random variable with respective parameter np and mp. So x is a binomial random variable with number of trials is n and probability of success is p. Similarly, y is a binomial mp random variable. Now, what is their sum? Is x plus y is again a binomial random variable? So this one we can do it with the same property, the convolution of their PMF. We can do that. So what is that? We'll do this one. So we know that convolution is basically the sum over all x. So what we can do, it is equal to P of x is equal to k and P of y is equal to w minus k. And then we have to do for all such k, we should have, right? So therefore k is equal to 0 to w. Now we have there, because x is what? X is a binomial NP random variable. We know that its probability mass function. What is that? It is nck p to the power k into 1 minus p whole to the power n minus k. At the same time, y is also a binomial MP random variable. So y equal to w minus k is what? It is mc w minus k p to the power w minus k and into 1 minus p to the power m minus w plus k. And if you just simplify it, you will be getting, like I am taking some term outside the summation because that does not depends on the summation. So if you simplify it, you will be getting this into 1 minus b whole to the power n plus m minus w, and then the summation over k equal to 0 to w nck into mc w minus k. Now we know that this quantity, this is actually okay. I can do that only. So this summation, it is an actually an identity. We call them as Vandermonde identity. It has a particular value. What is that? The value of this identity is actually n plus mcw, right? So this value of this term is n plus mcw, known as Vandermonde identity. And therefore we got, if I put that value, it is P of W is equal to W is equal to that value I am putting. So it is n plus m CW P to the power W 1 minus P to the power n plus m minus W. Now, can you see that? What is this? This value is what? We all know this. It is a binomial random variable. It is the probability mass function of a random variable, binomial random variable with parameter what? N plus 1, n plus m comma p, right? So therefore we got that x plus y is actually a binomial random variable, with parameter n plus m comma p. Got it? So therefore, if x and y are independent random variable with parameter np and mp, then x plus y is again a binomial with parameter n plus p, n plus m comma p. Right? So yes, this is the one as we have done it already. The whole group is very formal way. And therefore, we have seen that x and y are binomial, then their sum is also binomial. Then we should think about the other random variable also. We know several kind of discrete random variables, right? So then we'll discuss one by one. If x1, x2, xn are independent Bernoulli random variable, then with the same process, the way we have calculated for binomial, we can show that their sum x1, x2, xn, it is not only for 2, it is for all x1, x2, xn, their sum is again a binomial random variable. So x1, x2, xn are Bernoulli, independent Bernoulli random variable, then their sum is x1 plus x2 plus xn is a binomial random variable with parameter n comma. Then the next is if we have x1, x2, xn are Poisson random variable with parameter lambda 1, lambda 2, lambda n, right? And they are independent. Then their sum is a Poisson random variable with parameter lambda 1 plus lambda 2 plus lambda n. So these things you should know that if the individual independent random variable, what is their sum? And then we know the another one also. What is that? If x1, x2, xn are independent geometric random variable with the same success parameter p, then x1 plus x2 plus xn is a negative binomial random variable with parameter n comma. Right? So please note down all this sum. At least you should know the statement. And the proof of all this result can be done by using the convolution of the discrete random variable of their convolution of their individual PMFs. It can be done, right? Then there is a natural question that what will happen in case of a continuous random. So the sum of two independent continuous random variable, if you have, what will happen in case of their sum? Is it again a continuous random variable or not? So like is it again the similar kind of continuous random variable or not, we can discuss. So we can say what can you say about the sum of independent continuous random variable? What is that? Now, like the convolution property of the discrete type PMF, we can have the continuous convolution of PDFs. What is that? If x and y are independent continuous random variable with probability density function fx and fy, then the density of x plus y is given by the convolution that x plus y, that is w equal to actually a. Then in that case, it is not the summation but the integration. So take all x and fy of a minus x so that their sum is a, and take the sum over all x. So here it is that do the integration over x from minus infinity to plus infinity. So this is the uh, continuous convolution of PDFs because fxx and fyy are the marginal PDFs, right? So then the question is, if x and y are independent uniform random variables on 0, 1, each x plus y is again a uniform random variable. The answer is no, they are not. How? So if it can be proved, that again I am not doing the detail of it, you should know it. I'm just showing you that yes, if x and y are independent uniform random variable, then x plus y is not. Why? So if you calculate it, the range of w of x plus y is actually from 0 to 2. And its probability mass function of w is given by this function. It is a if 0 less or equal to a less or equal to 1, and it is 2 minus a if 1 less than a less or equal to 2. Right? And then we can easily see that it is actually not a uniform random variable. In fact, it is a triangular distribution over 0 to 2. Right? So from 0 to 1, it has this value, and from 1 to 2, it has this value. So it is a triangular distribution over 0 to 2. It is not a uniform distribution. So therefore, we can make the statement that sum of two independent uniform random variable on 0, 1 is not a uniform random variable or is not a uniform distribution, but it follows a triangular distribution. Then again, with a similar kind of a computation, one can also prove that the sum of two independent exponential random variable will not be an exponential, right? So sum of two independent exponential random variable will not be exponential. So in case of a continuous random variable, we have discussed about three type of continuous. One is uniform, another one is exponential, another one is what? Normal random variable, right? So then the question is whether for normal random variable also their sum is not normal. No, in that case it is not. So normal random variable is a special case. So the case which happened for uniform and exponential, this is not the case for normal random variable. Why? Just look at the theorem. If x1, x2, xn are independent normal random variables with parameter mu1 sigma 1 square, mu2 sigma 2 square, mu n sigma n square, then their sum is actually normal mu1 plus mu2 plus dot 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 mu n comma sigma square plus sigma 2 square dot 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 sigma n square random variable, right? So if x1, x2, xn are independent normal random variable, it's their sum is again a normal random variable, right? So in particular, if we take two random variable x and y, they are independent normal random variable, then their sum is normal random variable with parameter mu1 plus mu2 comma sigma 1 square plus sigma 2 square, right? So these are the things, again I'm telling you, one should know it, that what will happen in case of a sum of two random variables. So in discrete types, we have seen that yes, individually they were following something, that binomial means their sum is binomial, Bernoulli means their sum is binomial. Then we have seen Poisson means their sum is again a Poisson. And then the geometric random variable sum was negative binomial. Whereas in case of a continuous random variable, if they are uniform, two random variables are uniform, independent, uniform random variable, their sum is not. We also discussed that exponential random variable, independent exponential random variable sums is not an exponential random variable. Whereas in case of a independent normal random variable, their sum is again a normal random variable. Okay. Then we have another concept called identically distributed random variable. This is again a very, very important concept, but at least you should know the things what is there. So random variable x1, x2, xn are said to be identically distributed if each of xi has the exactly the same distribution, right? x1, x2, xn or x1, x2 up to any random variable, they are called the identically distributed if each of their uh, cumulative distribution function is same, if each of them have the exactly same distribution. So basically, if f of xy, fxx and fxi of x and fxj of x, if they are same for all x and for all I greater equal to 1, j greater equal to 1, we call them they are identically distributed. Right? One example we can show, let xi be the continued outcome of the ith toss, where xi is equal to 1 if head occurs and equal to 0 if tail occurs. So xi is the outcome of the ith toss. Then what about x1? x1 is equal to 1 if it is head, if the ith toss is head, equal to 0 if if the first toss is head, or equal to 0 if the first toss is tail. x2 is what? x2 is equal to 1 if the second toss is head, equal to 0 if the second toss is tail. Similarly, xn equal to what? Xn is equal to 1 if the nth toss is head, and equal to 0 if the nth toss is tail. And therefore, we can see that xi follows a Bernoulli distribution with parameter p equal to half, right? And then we can see, since all the toss follow the same distribution, then therefore they are identically distributed, because all the x1, x2, xn follow the same distribution, right? And now, if we have these identically distributed random variables, If they are also independent of each other, we call them are independent and identically distributed. And abbreviated, we abbreviate them as IID, random variable. Independent and identically distributed random variable, or IID random variable. Now this has a significance. That's the reason we are discussing about it. What is that? Okay. If x1, x2, xn are IID normal random variable with mean mu and variance sigma square, we know that x1 plus x2 dot dot xn is also a normal random variable, because we just now we have discussed, right? So sum of independent normal random variable is again a normal random. Now here they are normal. So we know that probability of their sum, because each of them have the same mean x1, x2, xn, because they follow the same distribution and they have the same variance. So their sum is n sigma square. Therefore, x1, x2, xn are normal random variable with mean n into mu and variance n into sigma square. Now, what we can say that the sum of x1, x2, xn, when they are IID, but not necessarily they are normal random variable, right? So they are IID, but not necessarily normal random variable. If you have that, we can say the famous theorem called the Central Limit Theorem. It says that if x1, x2, xn is a sequence of independent, identically distributed random variables, and each having mean mu and variance sigma square, then for large values of n, that means n is a very large number, x1, x2, xn is normally distributed with mean n mu and variance n sigma square. Right? So what we have, x1, x2, xn, or x1, x2 up to any number, x1, x2, xn are IID. Right? So they may not, they can be any random variable, but they should be IID. There should be IID. It can be discrete type also. It is valid for discrete type as well. It is valid for continuous type. So x1, x2, xn are IID. So independent, identically distributed random variable. Then their sum is for large values of n, their sum is actually normal random variable, normally distributed random variable with mean n into mu and variance n into sigma square. Right? So I just wanted to let you know the central limit theorem, the statement. You should know it. I'm not doing any example and all here, because later on, if you need it, I'll make some examples and little detail about it. Right? And then we can just standardize it, because we know that any normal random variable, we can make it standard normal by subtracting with its mean divided by variance. It is a normal 0, 1 random variable. Right? So this is the central limit theorem. And so this discussion, this lecture, I discussed about the sum of two random variables or sum of random variables, continuous and discrete type. We have done some observation, and then at the end we discuss about the central limit theorem. So you should know all this statement. You should know that we have not gone through the proof. We have not done much examples, but at least you should know them. Okay. So the references are this. Thank you very much. We'll meet in the next lecture.